Hello and welcome to the Plus podcast. I'm Rachel Thomas.
And I'm Marianne Freiberger.
In this podcast, we'll be exploring a crisis that is facing humanity. No, not the pandemic, although we have talked about that and written about that a lot in the last year. The crisis that is facing humanity is climate change.
Yes, but we won't just dwell on the awful facts and terrible predictions, but instead focus on the lovely mathematics that can help us predict the climate and therefore help us deal with climate change. And at the end of the podcast, as always, we will explore some cheerful mathematics in 1 minute.
If you know about climate modelling, or weather forecasting for that matter, you probably know that it requires incredibly fast supercomputers to crunch through the numbers. So that goes to show that these models must be hugely complex. Can we even begin to describe how they work?
Well, actually, yes, we can. There's one climate model that you could actually teach to people at school and solve more or less by hand. It's so simple. It's a so-called energy balance model.
Right, the energy balance model. How does that work?
It's based on the assumption that the Earth is in thermal equilibrium. So that means that the amount of energy the Earth absorbs from the Sun and the energy it radiates out into space exactly balance. So the two are equal. Now the energy that the Earth absorbs from the Sun, which is about 343 watts per square meter on average, but you have to take away from this amount the amount of energy that gets reflected straight back from the Earth into space before it is even absorbed. So, for example, that's the amount of energy that is reflected straight back from the polar ice caps. If the Earth was completely covered in snow, then around 80% of the Sun's energy would be reflected straight back. And on the other hand, if the Earth had just been freshly asphalted over, almost no energy would be reflected straight back. But as it happens, in reality, around 30% is reflected straight back. So that's what you get on the one side of the equation, around 70% of the energy from the Sun. That's the proportion of energy that is absorbed by the Earth. Now, on the other side of the equation is the energy the Earth radiates out into space. Now, that depends on the temperature of the Earth, because obviously the hotter the Earth is, the more energy radiates out, and the colder it is, the less energy radiates out. But it also depends on how energy passes through the Earth's atmosphere. That latter factor, how energy passes through the Earth's atmosphere, is measured by something called the emissivity of the Earth. So you can write all this down as an equation. Absorbed energy equals radiated energy. And the equation then gives you a relationship between the Earth's temperature, the emissivity, and the amount of ice there is covering the Earth.
Okay, I think I get that. So energy comes to the Earth from the Sun. Some of it gets reflected by the ice, the polar ice caps. Some of it gets absorbed. But the energy that is absorbed has to equal the energy that is radiated out from the Earth. Can you now do things like see what would happen to the temperature of the Earth when there is less ice?
Exactly. Say some of the ice on Earth melted so that now only 20% of the Sun's energy is reflected back. Then if you plug that reduced value for the energy that's reflected into the equation, then you will see that the temperature of the Earth in the equation also has to go up so that the equation is still balanced. So less ice leads to global warming.
And what if you change something about the atmosphere to affect the emissivity? For example, releasing lots of greenhouse gases into it?
Well, it turns out that that would lead to a smaller value for the emissivity. And if you plug that smaller value for that into our equation, then you will see that the temperature must also go up. So the equation shows a direct cause and effect link between the increase in greenhouse gases, such as carbon dioxide, and the rise in the predicted temperature of the Earth. And the equation also predicts a direct cause and effect link between ice melting and the temperature going up.
Well, that's pretty good for such a simple model. I must admit it's also a bit depressing since, as we know, we have put huge amounts of greenhouse gas into the atmosphere, and due to the rising temperatures that causes ice caps are melting. So the simple models tell us that both effects will further raise the temperature on Earth. But ignoring the depressing aspects, I'm really interested to know what the equation is. What's the equation?
Okay, so for those who are able to cope with equations in audio, here it is. The proportion of the energy reflected straight back is called the albedo. After rearranging, the equation says that the temperature of the Earth to the power of 4 is equal to 1 minus the albedo divided by the emissivity times a constant number. The constant number involves that incoming power from the sun we mentioned above, and another number called the Stefan-Boltzmann constant.
Brilliant! Now we know a simple model for understanding climate change. The simple energy balance model captures some of the key aspects of climate change, but if we want to be more precise, for example, if we want to know how climate change will affect different parts of the globe, how many extreme weather events will occur and where, we need something more sophisticated. Here is Emily Shuckburgh, mathematician and director of Cambridge Zero, the University of Cambridge's Climate Change Initiative.
If we're going to develop a more sophisticated understanding of the atmosphere, and oceans and climate more generally, we need to have a more sophisticated model of our climate system. And one of the key things about our weather and climate is that both the atmosphere and the oceans, in terms of their physics, are essentially fluids sitting on a rotating sphere. And there's something very interesting about the dynamics, the way in which a fluid on a rotating sphere moves and its properties.
That clip is from Emily Shuckburgh's recent virtual talk about climate modelling as part of the Cambridge Festival and hosted by the Isaac Newton Institute in Cambridge. And you can see her whole talk by going to newton.ac.uk and search for Cambridge Festival. During her talk, she showed what you get when you rotate some liquid with coloured dye in it in a tank. And it looks very similar to the Earth seen from space with its swirly cloud patterns.
And what I'm showing you here is a satellite picture. You can see the clouds swirling around in the atmosphere. It's a photograph taken from space. The next two pictures that you see here are laboratory experiments. And these laboratory experiments, you're looking down on a tank of water, and some coloured dye has been injected into that tank of water. And the difference between these two tanks is that on the left-hand side, the tank of water is just sat still on a table. On the right-hand side, what's the difference is that tank is rotating, just as the Earth is rotating. And as soon as you start rotating a tank of water, you can see that you emerging out of these rather beautiful swirling patterns that actually are rather reminiscent of exactly the sort of swirling patterns that we see in those satellite pictures in terms of our clouds. And that is essentially because the dynamics that is the most important aspect of determining the evolution of our atmosphere and our oceans is the fact that these are fluids on a rotating sphere. So we can actually use that to develop a model of how our atmosphere and oceans evolve. And the key aspects of that are that we have the motion governed by Newton's second law, that it's rotating and that we're sat on a sphere. And if we put those equations together, then we get a set of equations that are at the heart of all models of the weather and climate.
The equations that Emily Shuckburgh mentions actually come from a very famous set of equations called the Navier-Stokes equations. To predict the climate, or indeed the weather, what you do is feed in today's weather and climate data into the model as starting points, things like today's temperature, and air pressure, for example. And then the equations tell you how weather and climate is going to evolve, how it's going to change over time, given these initial conditions. It's a bit like using Newton's law of gravitation and motion to calculate the trajectory of a football that's being kicked with a given force. You know the initial condition and you know the equations that govern the motion to calculate what is going to happen as a result.
Okay then, so why does this need supercomputers for weather and climate?
Well, the equations involved in climate and weather modelling are nowhere near as easy to solve as the equations that describe the motion of a football. In fact, even very fast computers can only work out approximate solutions, albeit very accurate ones. Also, it's practically impossible to continuously measure the temperature, the pressure, the humidity, wind speed and everything else at every single place on Earth, and then to make predictions for every single place on Earth using your equations. So what weather and climate modelers do is to divide the space surrounding the Earth into a grid. It's a bit like the grid you often see on 2D maps of a city or of the whole Earth, only now it's a 3D grid that extends down into the oceans and up into the atmosphere, wrapping the whole globe. And then you start with the initial conditions at these grid points and calculate the forecast for these grid points only. This does make the calculations tractable, makes them doable, but still an enormous amount of computational effort is needed. As Shuckburgh says in her talk, to predict the weather, the Met Office takes in 200 billion weather observations from all over the world every day, which serve as the starting points for an atmospheric model that contains more than 1 million lines of computer code.
Okay, so what we learned so far is that both weather and climate modelling essentially work by solving a set of equations based on the famous Navier-Stokes equations on a grid, and that it takes a lot of computer power to do that. But what's the difference then between weather and climate modelling?
Well, that's the question we asked our friend Chris Budd, Professor of Applied Maths at the University of Bath, when we last saw him at the Heidelberg Laureate Forum.
A climate model and a weather model are all based on the same basic physics, and that's the Navier-Stokes equations which describe motion of the oceans and the atmosphere. In a weather forecast, you're using low, very small grids, so grids of about 1 kilometre, to get very, very accurate, high-resolution forecasts over short periods of time. Now, the problem with using such a small grid is that the computations are just impossible to do for long-term climate modelling. The other difference is that in climate modelling, we're not trying to forecast what the day-to-day variations are. We're looking at general trends over periods of decades or 100 years. So the sort of day-to-day variation that we get in weather is just almost noise on top of the more general trends that we're trying to do for climate modelling. The other big difference between weather and climate is that in climate modelling you're putting in longer term effects in the actual model. So, for example, the release of carbon dioxide, the motion of the ice caps, the change in vegetation, the absorption of CO2 in the ocean, all these things go into climate models. These are irrelevant for weather modelling because they're on such longer timescales. The sort of work I do, I'm looking at climate not just over 100 years, but over millions of years. And over millions of years, you have to put in the effect of the variation of the sun's illumination on the Earth, which is the dominant effect over those longer periods of time.
Now, one thing that we all know about weather forecasting from bitter personal experience is that it can be unreliable. So is that because the models, despite their complexity, are still not doing a very good job?
Well, no, there's another problem at play here, and that's the famous butterfly effect. It means that a very small discrepancy, say in your initial conditions, can, over many calculations, build up into huge discrepancies in your final predictions. So if you get your initial conditions at a grid point even slightly wrong, that small error can build up into a very large error as the computer crunches through the calculations to predict the forecast. We'll tell you more about the butterfly effect at the end of this podcast. Also, you have to keep in mind that the fact we're using a grid also leads to uncertainties, as there's processes related to weather, say clouds forming, that happen on a really small scale but can still have an impact on larger scales. So dealing with uncertainty is an important component of both climate and weather modelling.
Right, so I know, for example, that in weather forecasting, people often produce so-called ensemble forecasts, where they run the model many times on a variety of slightly different initial conditions, so that they then get a whole range of possible future weather scenarios. And meteorologists then use these ensemble of forecasts to figure out the most likely scenarios. So loosely speaking, if 10% of the potential forecasts say it'll rain, then the weather forecast you see on your weather app will say there's a 10% chance of rain. But what about uncertainties in climate modelling? How are they dealt with?
Well, uncertainty in initial conditions is a problem here in climate modelling too, but there are also uncertainties about the models being correct. Here's Chris Budd again explaining how you can still keep tabs on your models to gain some confidence that they're making good predictions.
The most important thing you do is that you compare the model against past data. So this is called hindcasting, where you run the model for a period of time and you compare its predictions against what you have observed in the past. And if you do that, that gives you some confidence. For modelling climate over billions of years, that's all you can do, because we can't wait for another billions of years to do into the future. But for other types of models, such as the global complexity models, where you're trying to predict over decades, it is reasonable to make predictions. So some of the earliest IPCC models did do predictions, so in the 1990s, as to what would be happening now. And to be honest, they've done pretty well. And so that allows us to check those models. They did make genuine predictions, which we are able to then check.
Now, if you look at reports issued by the IPCC, that's the International Panel for Climate Change, you'll find no claims that any more detailed predictions are going to come true with 100% certainty. Instead, you'll see scenarios that are likely to occur under different assumptions. But perhaps the most important thing to keep in mind in this context is that all the models used by the IPCC chime in their predictions for the overall climate of the Earth. They all say that it'll warm up, that ice caps will melt, and that the sea level will rise. There is no doubt about that.
Now, the maths underlying those climate models was developed over 100 years ago, but that doesn't mean that the science of climate modeling stands still, far from it. The models are constantly being improved. For example, as Chris Budd told us, one approach is to develop intermediate models that aren't as complex but still give good predictions. And another very exciting approach, which Emily Shuckburgh mentioned in her talk at the Newton Institute, is to combine climate modeling with big data.
So in terms of how we can start to push the boundaries still further in terms of our ability to improve our projections, one thing that there's a huge interest in is whether or not we can adopt not just physics-based modelling of our future climate, but inject data-driven modelling as well. And we have vast data sets now for how our world is changing, coming from satellite observations, coming from networks of sensors, all the ocean floats that are taking observations not just at the surface but down into the depths of the oceans, sending back their data via satellite. And there's a huge resource in terms of describing the current state of the oceans. We also increasingly have other sources of data. This is a project that's been looking, a citizen science project that's been looking at transcribing old ship's logs to get pushed back even further back into time, the records that we have of weather conditions. So how can we make better use of these great data sets of how our weather has changed in the past? And can we use new machine learning and AI techniques in order to be able to make better understanding of that data?
What Emily Shuckburgh means here is that in addition to including in the models what we know about the physics of climate, so for example the motion of fluids on that rotating sphere, we can also exploit all the information we have from this vast amount of data that's available. An example Emily Shuckburgh gave in her talk is of some work where the daily average summer temperature in Chicago between 1980 and 2019 were compared to predictions of climate models run over the same period.
What you can see is that the climate model does a reasonable job of replicating the actual observed temperatures, but it's biased warm. It's predicted that there would have been more warm, very warm days than there actually were observed to be. And if I'd shown you a different model for the same location, it may well have been biased cold, or if I looked at a different location, it might have been biased warm or cold, but they're never an exact match. And so what we've been looking at is whether or not we can learn that mismatch between the observed, the actual data that we have for a particular location, particularly focused on understanding the more extreme weather events, the bias between that and the models, and use that to apply a bias correction that we can also be applying to the future projections as well. So we can essentially learn a way of producing a better projection into the future that is consistent with past temperatures.
And when Emily Shuckburgh says learn here, she means not a human sitting down to learn, but a machine learning algorithm learning to spot patterns in the data of the discrepancy between real temperatures and model predictions. The idea is that this kind of data-driven modeling, together with the physics-based modeling, might be particularly useful for improving model predictions about localized extreme weather events, such as floods or heat waves, for example.
To find out more about machine learning, go to plus.maths.org and search for machine learning. And to see Emily Shuckburgh's Newton Institute talk about climate modelling, go to newton.ac.uk and search for Cambridge Festival.
We have now come to the point in the podcast where we explain some maths in 1 minute. So, Rachel, can you please explain the butterfly effect in 1 minute?
Yes, no problem. The term butterfly effect describes the fact that even tiny discrepancies can snowball into huge errors over the course of many calculations. And the name comes from the charming thought experiment that an air current set in motion by the flap of a butterfly's wing could eventually build up to cause a hurricane on the other side of the globe. Mathematically, the correct term for the phenomenon is sensitive dependence on initial conditions. And here's why. So you take a simple equation like y equals x squared. Let's stick in some value for x and see what we get. So if we take x equals 2, then y equals x squared equals 2 squared, which is 4. Now let's apply the same formula again to our result, which is now 4. So 4 squared is 16. You apply the formula again, you get 16 squared, which is 256. You can see where this is going, starting with an initial value of 2 and applying the formula again and again to the results you get gives us larger and larger values. And the sequence of numbers you get is 2, 4, 16, 256, and eventually it gets enormous off to infinity. But what happens if I start with an initial value of 1? Well, implying the formula x squared the first time gives us 1 squared, which is 1. Applying the formula again gives us 1 squared, which is 1, and so on. So starting off with the initial value of 1 and applying the formula again and again just gives us a repeating sequence of 1s. So that's a pretty different outcome depending on whether you started with 1 or with 2. So if you imagine that our initial value was, say, the temperature today, and the value you get after a number of applications of the formula was that temperature in some number of days, you can see that getting your initial value wrong by just 1 degree would lead to vastly different temperature forecasts in the future. In the first case, if your temperature was 2 degrees, the temperature would rise at some alarming rate, and in the second case, it would just be stuck at 1 forever. We should say at this point that our model involving squaring does not apply to the real temperature on Earth. We just use this simple formula as an example to illustrate the butterfly effect. Now you might say getting the initial value wrong by 1 is quite bad, and surely we can be better and get a more accurate estimate of the initial value. But the point is the butterfly effect will not go away. Even if I get my initial value wrong by just 0.00000001, one forecast, the one where the x is 1.00000001, will result in a sequence of numbers that eventually goes off to infinity, while the other, the one with x equals 1, is stuck at 1. This sensitive dependence on initial conditions doesn't just turn up in the quadratic formula, but in all sorts of expressions, including the ones that are used in weather and climate modelling.
Well, thank you very much, Rachel, for this clear and brief explanation of the butterfly effect. And it brings us to the end of this podcast. We would like to thank Chris Budd and the Heidelberg Laureate Forum, where we talked to him about climate modelling, and Emily Shuckburgh and the Isaac Newton Institute in Cambridge for Shuckburgh's talk on climate modelling. And if you'd like to find out more about climate modelling or machine learning, or see any other articles by Chris Budd, then please go to plus.maths.org. Thanks for listening, and bye-bye.